My name is Barak. I'm a principal engineer at Traverse. I've been working on lakeFS for more than 2.5 years. And in this talk, I would like to dive into how lakeFS versioning engine actually works, and hope you can gain insights from our process while building this engine. So at the beginning, we had a very short list of a wish list or requirements that we wanted to gain. The first one was cheap branching. As you saw in Tal's talk, one of the main capabilities is branching. And having cheap branching is a way for us to prevent from you copying your data in your production or your bucket into a way that can continue work while using lakeFS. And because those changes should enable you to read and write this data, this operation should be fast enough, because any product that we currently use which will fail in this item will probably be dropped along the way. Efficiency in diffing and merging as part of the versioning engine is a core capability. Without knowing which changes are getting into your branch or going out is very crucial in having a versioning engine. And of course, we wanted to use the same concept that we already knew from having a versioning tool like Git in our versioning engine. So we look at how Git does it. This is a very known chart from the Git internal documentation. As you can see here on the right side, there are blobs. These are your files. Each file is kept with the same name based on the version, on the hash of the content of your file. So for example, if you are using version 1, you will get this blob, and if you are changing the content to version 2, you are getting this blob. Each directory represented in Git is represented by an object called a tree. A tree will point to the object found in the same folder. A tree as a folder can include other folders. So if we look at the third commit, we will see a tree that will point to 2 existing objects and one folder that was holding one object in the first commit. So it's very dynamically, and by pointing into a root tree, we are getting a single point where you will traverse your current object in your versioning control. So the concept that your data is accessible by the version, the hash value, and the pointing of tree collections as a tree hierarchy is what we did. We implemented the version 1 of the engine, and we described the existing of your bucket using those trees. The good news, it worked. The same concept like getting a branch, accessing the bucket, and have it with very cheap milliseconds creating a new branch worked, but it didn't work fast enough. What we ended up finding ourselves is traversing over and over a tree hierarchy as your file system in a bucket, but a bucket is not a file system. A bucket uses a flat hierarchy. Listing a bucket means that we, as a versioning engine, had to traverse all the folders as it's virtually implemented in order to list information that is currently on the underlying storage. Another key issue we had is that a single tree on a file system that is represented by a directory can hold a number of files, but in a bucket, it holds millions. For a versioning engine where we need to maintain metadata information that represent that folder, meant for us to rewrite every time the tree with the new or updated information, which took time, which meant we weren't fast enough. So we took those key issues. We learned that the traversal and the size of the tree is an issue for us. We understood along the way that the part that we saw already from the previous talk by Tal, that the data lake changes, but not the complete lake was changing, was working for us. And we thought about how can we perform better? Which change we can introduce to get a very small response time and manage those information. So we thought about, let's add a database, a rational database. At the time, we used Postgres, and like any good developer that saw something that worked, we took all the metadata from the underlying storage and created tables and inserted it into the database, and coded like crazy, big SQL queries, and the good news, it worked. It was very cheap branching, it was the same referencing, and this time I was just querying the information from the database. The listing was working fast, it was a very, until one point it was working very fast, and it failed. It wasn't predictable. In some cases, because the query engine the database is using is based on cost-based optimization, there are cases where the database was choosing sequential scanning over using a specific index. So we found ourselves battling against an SQL engine to work as we expected as a developer to work in some cases, managing the database to do better statistics or finding bits and tricks over SQL to make it work fast. So we thought about what we can learn. We understood that if we put all the metadata in the database, we can get very lower response time while doing very simple operation, but having complex queries where the data gets to our service in unexpected performance, it can't hold. We understood that we want to manage code and not SQL statement over time. We understood that having all the data in a database where it doesn't change a lot. As we saw before, many of the data in your lake doesn't change over time, and we still go to an SQL query to get it because latency that we didn't thought about. So in version 3, and this is the last version, we introduced a different change. We used a key value database. This helps us maintaining all the mutable data, the uncommitted data, the references, and gained the performance we wanted when accessing in a simple pattern and not going over millions of objects for a metadata. For the metadata we keep for committed data, which is immutable, we wanted a different data store, data structure. We wanted an immutable data structure that will represent the complete data lake, a snapshot, the point that the commit will look at when it needs to understand what is currently kept on your bucket. This data structure should enable us fast lookup and lexicographic listing to enable fast list operations. And when we introduce changes to this immutable data, it's funny because it's immutable, but we need to introduce changes, it should enable us a predictable performance based on the change we are going to introduce. Having that fact that the data doesn't change there, we can store it on the underlying bucket, same place as your data. So this is what we came up with. If we will look a little, if you will remember from the previous slides, it's very similar to Git. We have a branching pointing on commits, and commits will point to a layer. You can see it's called meta range and ranges. This is the index layer where it's pointing to the actual data in your lake. So if you remember the Parquet file or any file agnostic information, it is kept on the bucket, and I have a slide saying where the data is kept. And you can see that all the meta range and ranges, we will drill down to understand how they are keeping the data as we designed. And all the mutable data, uncommitted data, and commits for performance reasons, we kept on the key value database. So what's a meta range? We took the same concept as Git. That means that the content of the meta range is kept in the same location based on the value, on the hash value of the data. That means that if I'm looking at the same thing, I'm looking at the same file because I'm looking at the same content. The meta range itself represents the complete metadata information in your lake because we can't hold a single object that includes millions of metadata records, we split it into ranges. So we are getting a B plus tree-like data structure. Each object, the meta range and the ranges, are kept in an SS table RocksDB format, hence the name Graveler, if you like Pokemons. And if we drill down into the range, you will see that it actually holds the metadata that the versioning engine manages. It's a lexicographically ordered metadata information, the logical location of the file, and the metadata that includes the physical location of your actual data. The range is also hash content addressable, and the size, if you remember at the beginning that we forge Git-like trees, is now controlled by lakeFS. That means that we found out that for us, 10 megabytes of range size is an optimal size that we will like to manage as a single range. That's enable us to incorporate changes easily, because when a change occurred into your lake, only specific ranges will be updated. Let's take, for example, adding 2 files to an existing commit. The gray boxes represent a commit where a meta range points to a list of ranges, which represent a complete state in your data lake. If we like to add those files, in this example, it started with an I, which means that the range that we need to update will be H to J. This range will be rewritten. Of course, we will not run over it because it's based on the content, and the hash will be different hash. So a new range is introduced that will include the 2 files. A meta range will reference all existing ranges except the one that we just updated. And this way we can commit very, very fast, because we are not writing all your metadata again and again between commits, and the size of the change depends on the size of the change and not the size of your data lake. And this is how the versioning engine attacks Diff. So Diff is basically a set operation. We have 2 meta ranges with an ordered hashes that represent ranges. All the common ranges can be skipped. It means we are pointing at a range that represents a part of your lake that didn't change. So we can skip a lot of the metadata while we're diffing between 2 commits. The different ranges that are not common in those 2 meta ranges will be drilled down and do the same operation, just in the object level. So in this example, those 2 ranges diff will find the 2 files we just committed in the previous slide. A workspace. A workspace is the equivalent to the staging area, because in lakeFS you work remotely on your metadata engine. We need to maintain all the uncommitted data. So a branch will point to the last commit and will hold a token that will represent the changes you're currently doing on your branch. So for example, when in the previous talk, we explained about experimentation. So all the changes before you commit will go to our key value database, and only if you commit them, we will scan and generate the relevant metadata, the meta range and the ranges that represent that change. So from this diagram, you can see that having a new branch is simply an entry in your key value database. I just need to specify that I have a new branch which references existing commit, and it got a new token for the future changes, and you can continue to work. This is why lakeFS is very fast in creating branches. Okay, let's go over our goals. So as described a second ago, new branch is very, very fast. We are not copying any data, we're just referencing an existing metadata. And we use the fact that the data structure that represents most of the data on your lake is immutable, cacheable, and we control the size of the part we like to manage. That's enable us also, because the format of the each block is ordered and can be fast lookup. That means that the main operation, like listing, getting information, is very, very fast. Using the two-layer B tree, we can support very, very fast diff operation, skipping common changes. Most of your millions of objects can be spared in comparing what changed. And by introducing the meta range layer, we can also reuse the existing ranges that describe the data lake in order to perform fast merge operations. And of course, every operation you know from Git, almost everyone, every operation, revert, diff, merge, commit, and branching is core capability of the engine itself. And that's it. We have questions? Oh, no. The data we are referring the metadata storage for us. The meta. I'll repeat the question. Question was about if we are splitting any data into 10 megabytes. We are not touching the user data. This is only relevant because the meta range and the range holds only metadata. This is and we can control the meta range size, but it only references to the existing ranges. We are trying to control the range size, which holds the actual metadata information. That's the case where we didn't want your folder size equal our range, because it causes latency issues. Every object, if it's small, it's bad, because if you upload something to S3, you need to wait, I think, 15 milliseconds for first byte when you read it. So we need to have some size that, we need some size that is very comfortable for us to split and reuse, and not big big to make it issue for us to rewrite and wait to upload to S3 or any other underlying storage. So the question. So the question is, how do I start using lakeFS if I'm currently having petabytes of data, and how do I go back? So lakeFS manages metadata. It's a metadata versioning engine, and one of the core capabilities for onboarding data is importing. So what we did in importing, we supported importing for external source. So if lakeFS has access to your data, you can import existing data without copying any data. That means that if you will look on the underlying implementation, we will point to your data. That means that, for example, retention will not work for your files, but you will have initial commit saying this is the data I imported into lakeFS, and it is accessible from lakeFS as long as it got permission to access your bucket. If you upload data through lakeFS, the data will be kept under the bucket you created for lakeFS under the repository path, and it will be managed by lakeFS. So it's like iTunes. I can manage your music, or you can let me manage your music. Okay. Other questions? Yeah. Mm-hmm. So good question, because any generation handle it differently. Where two Spark jobs commit at the same time. What happened? So let's talk about practices and then real life and what happened in real life using the versioning engine. So we try to say that you would prefer a single committer because it's optimistic. I will fail one of them and it will retry. So because it's an history, it's Git. One of us, if we are committing to the same branch, one of us should fail. So in most of the cases, the practice for us is that each writer can branch out, write the data, merge back, and continue the work.
So there is no concept of conflict, it's just...
Oh, yeah, there is conflict because you can merge back, and if it's you introduce a different change to the same file, you will have a merge conflict.
Just if it's the same file?
Yes, any change to the file will change the checksum, and if you are pointing at the same logical path, it will be conflict because we don't know which change you wanted to introduce. So if we are talking about conflicts, it's if you are writing the same thing. If we are talking about specifically commit, because the commit log is a single thread. Every time you commit, I need to understand who is the father of the commit you just did. So if two processes coming at the same point and try to commit, one of them will succeed and change the reference of the branch saying, I'm the last commit. The second one will try to do the same, will almost finish the commit, and then he will find himself saying, okay, you weren't there when I started, and we will do it again. So basically, we are optimizing a lot of the processing while committing, so most of the meta ranges and ranges will be in place. So, and we are optimizing the process as we go. And it should be that the retry over time will be faster, but we still can have atomic 2 commits at the same time at the same branch. Okay, so how data is exposed or ingest using other tools. So lakeFS, there are good question because there is multiple solutions, of course. API is open API spec, which is lakeFS, but lakeFS listens and provide S3 compatible interface for lakeFS, not just the underlying storage. If lakeFS is here, lakeFS can work with different underlying storages, any compatible S3, Google, Azure, but it also provides S3 gateway. That means that you can access with any compatible S3 tool to lakeFS directly, given the credential you have, and you can read, write through lakeFS all the data you just saw. And
S3 pass, so branch will be put?
You just point the S3 endpoint to lakeFS, give it the S3 credential, and your data on the repository will look like S3 with branching path. And we also come with a library for working directly with Spark, because we can optimize working with data. That means that your application doesn't go through lakeFS to read or write the data layer. If you are going to write to S3, the library will enable you to write directly to the underlying storage, and that leverage the current capabilities or outgoing network to be the same as you are currently doing, and just the metadata change will introduce through lakeFS. So for example, I can work directly with lakeFS and treat lakeFS like S3 bucket, and I can incorporate, for example, Spark library and have the Spark writer commit directly to the underlying bucket and let lakeFS know which metadata changes should be introduced. Okay, I hope you enjoyed. Thank you.